In today's lecture, we're going to continue with where we started last time, discussing private machine learning. Today, our focus is going to be on more modern machine learning and practical machine learning approaches. We're going to cover two main approaches today. First up, we're going to cover a private stochastic gradient descent. This is roughly the same place where we left off, but looking at that method modified a bit and with some better analysis as well in order to work in more practical settings. And the second will be a method which is based on private aggregation of non-private learning methods. But before we get into that, let's talk a little bit more and give you a bit of a primer on some of the modern machine learning settings, including neural networks. This isn't going to be crucial for the later parts of the lecture, but at least I think it's a good thing to know if you're not familiar, and it might be good to see why some of the methods which are used in modern machine learning are not really amenable to the type of methods which we discussed in previous lectures, and where the analysis really fails. So, okay, we're going to only discuss and introduce the most basic class of neural networks known as multi-layer perceptrons, or MLPs for short. So other classes are similar, other neural networks are similar, but you might just swap in some different layers and it'll roughly be the same. So remember, as before, we have a data set D, which has XY pairs, loss function L. And the goal is to find a parameter vector which minimizes the following quantity. We have the empirical loss. And this is just the sum of the loss functions over the entire data set. That's the sum L theta xi yi I and n. So yeah, this is the exact same as what we had before for now. But let's see what the setting is for neural networks. So before we proceed, let's just suppose that the data domain that we have, that x is in, say, r to the d, and the label space has y in k. So that means that there's k different labels. So if it was binary, then k would just be 2, because we could have y equals 1 or y equals 2. But yeah, we're going to say that y is, say, a number in 1 through k. So what does a neural network look like? I'm sure many of you have seen this type of picture before. Let me kind of draw what it looks like. So this is the input, which will be something like x. And what we're going to have, I'll synonymously call it, this is V0. And we're going to have other future layers, stuff like this. And, these will be, this is how you usually draw it, and I'll just draw this first, and then we'll discuss sort of what it means. Just go on. And then let's say we have just, I don't know, say 2 outputs here. So the idea is we have these different layers. So there's like the first layer, there's the second layer, and there's the third layer. And the idea is each layer that follows will be essentially a linear combination of the previous layer. So this is V1, and this is, say, V2. And then we're going to apply what's called a nonlinearity. So let's just, this is a lot to throw at you at once, but let's write first mathematically what each layer, how it can be expressed. So each layer, say, V of I is equal to, I guess let me just note here that this is in the case where, say, D equals 3, because the first layer is dimension 3, and then the last layer is going to be dimension k equals 2. So we can write what the expression is for each layer in terms of the previous layer. So this is just something like the following. Some function here, fi, of a weight vector, or a weight matrix rather, times the previous layer. plus some, say, offset I. So essentially all this is doing is what it does is it takes yeah, let me define some of these. So we have vi is sort of a parameter vector, or sorry, not a parameter vector. This is going to be something which is in, say, r to the mi, where mi is the dimensionality of the ith layer. And we have that the parameters here, like the parameters, that is, you know, the theta, the things we're trying to learn. Theta in this layer are going to be the w sup I, which is in r to the mi times mi minus 1. The reason being that it kind of is a linear mapping, which takes us from being the dimensionality of the I minus 1 layer to the ith layer. And we have that b of I is in r to the mi. And so these here are the parameters. Now you might be wondering, what is this weird function f here? Well, this is going to be, up till now, this would just be a nice simple linear combination of the inputs, and then future layers would be linear combinations of the previous layers, and therefore we would just have a fully linear network, and it would be much easier to deal with. But the tricky part is the fact that, what is this f here? Well, this is going to be what's known as an activation function. This is a fancy sounding name, but really, it really just means something like, it just means a function which takes in something and gives a new value. It's not totally clear. Let me say it a bit more precisely. So fi, this is going to be a function which takes in a real number and outputs a real number. Note that I'm doing a slight abuse of notation. This is going to be a vector, but f is applied entry-wise. Yeah, I'm just using this as a shorthand to say that we apply to each element of the vector. But okay, fi is f to the I is a function which takes a real number and outputs a real number, and these are typically nonlinear functions. For example, a common nonlinearity is the ReLU, or the rectified linear unit. Which has that f of x is equal to max of 0, comma, x. So to draw this as a picture, it looks something like the following. So this is the x-axis, and this is the y-axis, this is f of x. So this is just going to be flat here, and then it'll be linear. So yeah, it'll essentially take this vector, and for entry-wise, if something's negative, it'll just zero it out. Otherwise, it'll let it through straightforwardly. There's other standard ones as well, which are used. This ReLU is by far the most popular. But there's others which used to be more popular, but have fallen a bit out of fashion nowadays. Things like sigmoid and the tanh. This is like, has f of x equal to 1 over 1 plus e to the minus x, and tanh is like equal to e to the x minus e to the minus x over e to the x plus e to the minus x. So these are two different activation functions which are also used, and they look, we won't belabor this too much, but they look something like the following, roughly, you know, something like this type of shape. This is not perfect picture, but like that's the rough idea of what they look like. Notice they're kind of different from this. But yeah, ReLU, like I said, is by far the most popular one, and what most people use in practice nowadays, seems to be most effective. Yeah, for reasons that are technical, which I won't get into here, but things such as, you know, I'll just say some words and you can look them up if you're curious and want to know more. But things like vanishing gradients are an issue with, say, sigmoid and tanh, but not an issue with ReLU. So yeah, this is roughly what a neural network looks like. It will, have some input layer. It'll take a linear transformation of that vector and apply some nonlinearity entry-wise to obtain a new vector, and just does that again and again and again. And a lot of modern machine learning has been really fueled nowadays by making very, very big and very wide and very deep layer networks of this form, which seem to get surprising levels of accuracy on modern machine learning tasks. Things that people didn't really believe that we could do with such high accuracy before. So yeah, let's just note that we still want to return this back to our previous setting where we were looking at empirical risk minimization. How do we really deal with, what is our prediction here, and what do we do? Well, yeah, we haven't talked about the prediction yet. So we just have this input vector, and it does some transformations, and it'll leave us with some other vector, say v2. Let's define the last layer. So the last layer will be O, and this will be, like I said, O is in, O is dimension k. Dimension of O equals k. And remember, really what I'm trying to do is just say that we have one node in the last layer for each possible outcome. So yeah. Now, these will just be some values, but what we want to do is try, the values in the last layer, the vector O, will just be some values, but we really want to somehow map from these values into a prediction. That is, we want to say, okay, is it going to be k equals 1, or is it going to be k equals 2? Well, it's not necessarily clear how to do that, maybe. I mean, I guess a natural way is to try to choose the k which has the largest value, or sorry, the index which has the largest value there. Like, is O of 1, is O1 bigger than O2, or is O2 bigger than O1? Well, what we'll do is actually do a transform. We want to really pick the argmax, but we can't necessarily always do that. So instead, what we're going to do is we're going to convert this from some arbitrary vector into something that looks like a probability distribution. That is, we're going to take O, and we're going to have the prediction vector y hat is equal to what's known as softmax of O. Yeah, what do I mean by this? Well, this is going to be the following type of vector, where y hat of I is equal to the following quantity. It's going to be x of O sub I divided by summation of x O sub j, sum over all j and k. So the idea is, well, one thing we could have done is if you just put OI divided by sum of OIs, that would have normalized it. That would have made it so that it adds up to 1 if you look at it. So that would be kind of a valid probability distribution modulo the fact that some entries could be negative. But what we're really doing here is we're trying to make it so that things which were large before, say one thing is bigger than another, we want it to still be much, much larger than before. So we kind of, yeah, we kind of like it's called softmax. So we're trying to find the max, but the problem with the max is that it's not really, it doesn't have nice properties such as the discontinuous function. So really instead what we do is we just take an x which is much nicer, and it'll lead to something kind of that looks like a max, but not perfectly. Yeah, and like I said, this will have the interpretation that you can think of y hat as a probability distribution over the labels. You can think of this as being the network's prediction, a soft prediction as to what the label of the image is. For example, you have some input which you feed into the network, and the true label is going to be either, say, 1 or 2 or 3 or 4. But this kind of tells you a confidence of how sure the network is that it's a particular value. Say, if it could be that the y is going to be just 1 in one coordinate and 0 everywhere else, which means that's very, very confident that that's the right label. But it could also be something which is more uniform, in which case it says, I don't really know. It could be any of them. So this is how we define y hat, the sort of prediction of it. And once we have this prediction vector, we can just say output the max of this, and that will be a choice for a label. But it's also fine to say that this is our prediction, like output that. It kind of gives you strictly more information. All right, so now we've defined the model. We've shown how if you give it an input x, how it can come up with a prediction y hat. And we've defined what all the vectors are, but let's talk about what type of loss we have. Well, we have, like I said, we need a loss function, L of theta x y. What is the loss function? How do we measure how wrong the prediction is with respect to the true label? Well, it's going to be using something which is known as the cross entropy loss. Typically, you can really plug in whatever. You can plug in the L2 loss as well, but this is really the one that's used kind of because like the maximum likelihood here. So the loss function is the following. Yj hat, where, so this is the loss function for a specific example, x comma y, where we take y to be the one hot vector. So yj, I guess I didn't choose great notation here, but y, the vector y is equal to 1 in the coordinate of the true label, and 0 elsewhere. So yeah, the idea is that this is going to be okay for the sake of computing what the loss function actually is. We can just say that this is equal to the log of y hat of j, where j is the true label of it. But for like differentiability reasons and computing the gradient reasons, we're going to write the loss function like the following. So essentially, it kind of, yeah, it looks at sort of how much probability is assigned to the correct label, and it transforms it appropriately. Cool. So yeah, that's the loss function. And you might be wondering, okay, usually don't we write the loss function somehow in terms of the parameters? Like where does theta appear in this? Well, theta is kind of implicit in our definition here, because recall, what is y hat? Y hat is defined as softmax of O. What is O defined as? O is defined as kind of a linear combination of the previous layer with this nonlinearity, and then so on. So really, you can think of this y hat as it's doing a lot of work here, in the sense that it's hiding the entire architecture of the network, which we're differentiating with respect to. That we're representing the entire parameter vector using this y hat implicitly. Okay, so as mentioned before, this description corresponds to a very simple neural network, one which is just known as a multi-layer perceptron. There's other things you can do involving, say, like choosing more carefully which connections here are going to be 0 versus not. That's known as, sometimes, if you do it right, a convolutional neural network, and so on. But really, this isn't really too important for our discussion today. I just want to introduce you to some basics if you haven't seen them. And highlight to you some of the things which make them tricky. In particular, why don't our algorithms that we discussed in the previous lecture just work fully and all the time? Well, they're not nice in a number of ways, in the sense that we don't really understand them very well. For example, one thing is the fact that this loss function, on this case, this is non-convex. Like, we know very well how to optimize convex functions, but optimizing non-convex functions is a much trickier thing. And in particular, just the analysis that we used last time is not going to be relevant here. In particular, nothing I'm going to mention, most of what I'm going to mention today doesn't actually have any provable guarantees in terms of it, in terms of accuracy, but nonetheless, it's still going to just work in practice. That's kind of, I guess, in large parts of machine learning right now. We don't fully always have a good idea of why things work, but they kind of just do. So yeah, that's why I said today's will be a little bit more focused on the practical parts, because we don't really have some of the theory behind why some of these things work, though people are building it, so it's not totally hopeless. Yeah, in particular, SGD, stochastic gradient descent, in the non-private setting seems to be very effective at optimizing neural networks, despite the fact that they are not a convex loss function, and they're not necessarily performing convex optimization here. Another issue is the fact that last time we required our loss function to be Lipschitz, which is not the case here. We needed this loss function to be Lipschitz just so that we would be able to have an absolute bound on the L2 sensitivity of our gradients. So we didn't have that before. This time what we're going to do, we'll talk about this a bit more in the next segment, but we're simply going to clip our gradients. That is, if they're too big, you chop them off to rescale them, and that'll be okay. And we'll sort of artificially limit the sensitivity in that way. So yeah, that's it for sort of a quick primer on neural networks. We'll pick up in the next part with talking about DPSGD.